Hello and welcome! On the bench today we have two faulty modular power supplies, and in this video we're going to fix them. Now, we worked on one of these power supplies on a previous video, which I recommend you to watch as there was quite some magic smoke released and quite a few faults to deal with. At the end of that video we ended up with the power supply outputting 12 volts and 24 volts as expected, but the power factor correction was still not working. Now, after that repair attempt, I decided to do a little international collaboration with Marian, aka DJ Marek78. Marian has always been very helpful with my projects, so I sent him the power supplies and he fixed them for me. Or at least that was the plan. Marian did a stellar job with the repairs and he made 2 repair videos on his channel for you to enjoy. Marian is Romanian, but he recorded the videos in English for the first time, so please take a look at DJ Marek78's channel and the repair videos. They're linked down below in the description. Leave a like, a comment, and most importantly, do enjoy the videos. They're going to be cool. Marian managed to reverse engineer those power supplies. So my plan today was to just test the power supplies and maybe see if we could find a mitigation for what seems to be a common fault with them. But I had to re-record this intro as things didn't go as planned, and I ended up fixing 4 additional faults on these power supplies. So let me thank today's sponsor, PCBWay, and now sit back, relax, and enjoy the video. Alright, first thing first, I'd like to test the power supplies as they are, make sure everything works, and then we'll do a power test at 400 watts. The Fluke is reading 12 volts, the Kaiwitz is reading 24 volts, I have nothing connected to it. We will connect something, my electronic load, to these chunky wires that I prepared for the test, and I built some connectors, proper connectors this time, to basically tap into the logic of the power supplies. By the end of the video I'd like to check some of these outputs, like the fan logic out, which should be able to sense whether the fan is working or not. Right now I've got this little on-off button. The schematics for controlling this are on the datasheet. So first thing first, let's power this up, make sure we have 5 volts standby. 3, 2, 1, go. And we do have our 5 volts standby, so everything works fine. Let's turn this on and see what we're getting. Turn on, 3, 2, 1, go. We got the fan running, I've got 12 volts and 24 volts, so everything works totally fine. I'm not really questioning DJ Marek78's skills, it's just these have been traveling internationally and there might be some damage, so I want to make sure that everything works. The other power supply, by the way, has some damage, so we'll see that in a minute. But right now, this is all working. Let me plug my electronic load and we'll start testing these things. My new electronic tester is wired to the power supply on the 12 volts line. You can find a review of this tool on this channel. It was like, yeah, it works, but with a little asterisk. So if you're interested in this electronic tool, you might want to go and watch that video. I'll test the 24 volts line later on. For now, we'll go ahead and test the 12 volts line. Let's turn this on, 3, 2, 1, go. And let's turn on the digital load, which is set to 1 amp. There we go, we got 12 volts. Coming out of the power supply. And now let's test the power supply at its rated maximum, which is 34 amps. I think actually I'll keep it at 33, just to be on the safe side. Everything so far so good, the voltage is fine. And yeah, I don't see any issues here whatsoever. So this power supply is working totally fine. Fantastic, let's move on and test the 24 volts. Bearing in mind that at 24 volts this power supply can only output 10.5 amps. And we are at 9 amps for a maximum of 10.5. Everything seems to be fine, the voltage is stable. 12 volts is 12 volts, I don't feel anything wrong. Again, it's much less current than on the 12 volts line, and it seems like this power supply is working totally fine. Everything looks good. I think we can move to the second power supply, but I don't think I can test it out of the box. We'll need to open it up and fix some shipping damage, unfortunately. Let me show you. I think something went wrong during shipping and the mains connector here, I think is taking a hit. So reluctantly I'll have to open the power supply. I was hoping not to have to open them and test them out of the box, but hopefully I can see what happened by just removing the fan cover here. Alright, yes, the connector's taken a hit, but I don't see any damage. Maybe some little bit of plastic ripped at the bottom, but I think it's nothing really serious. I'm going to remove the connector, straighten it and solder it back. I think it's the best way. What about feeling? Oh no. And I thought this connector was gone, but no, it's still recoverable. Contacts used for mains are still intact, they're just bent. And then we have two extra pins, which are not connected to anything. They are basically fused inside plastic that came off while desoldering them, and those are bent as well. Not a big deal. I can use some super glue maybe and reattach them, but those are only there to give a little bit more stability to the connector when it's being used. But what matters is that my 240 volts pins are in good shape. I just need to straighten them up and reattach everything. The power supply is back in one piece and it's ready to be tested. 3, 2, 1, go. And that's it, we got 12 volts and 24 volts, so that is totally fine. But let's turn on the load. And here we are at 33 amps, which is 1 amp below the maximum. We got more or less 400 watts. The voltage is correct, no issues whatsoever, and it seems to be working totally fine, which is great. And we are back to where we were before, but this time wired to the 24 volts line. And here we are at 9.5 amps, so again 1 amp below the maximum, and this power supply also works totally fine. I had no doubts in DJ Mark 78 skills, but I had to make sure that everything worked, especially after being bumped around during shipping before returning to their owner. And now that we've established that these power supplies are working totally fine, we can open them up and see whether we can do anything to mitigate this issue. And we have already spotted something that we think can improve the situation here, so keep watching. Now what you see on screen is the offline switcher chopping off that DC voltage that is being generated by the primary section. Now in a nutshell, the way a switch in mode power supply works, and this little IC we are probing is a switch in mode power supply on an IC, is by chopping off, by switching DC voltage through a small transformer, which on this board is on the other side. So the 390 volts DC generated by this primary section are being switched on and off through the little transformer. Now when current flows into a winding, a magnetic field is being generated. So when the chip is closing the circuit, we have 390 volts flowing through the transformer and a magnetic field is being generated. This magnetic field is being picked up by the other winding, the secondary winding of the little transformer, that turns into a voltage itself, which then gets rectified and smoothened into a lower voltage. By keeping this switching at a very high frequency, I think this IC is running around 66 kHz or something like that, we can keep the size of the transformer smaller. Now on the waveform on screen, you can actually see this behavior. I'm probing between drain and source, so when the MOSFET is open, so there's no flow of current, you can measure 390 volts between drain and source. And that can be seen on the waveform that we have on screen. You have more or less 390 volts being measured between drain and source, but when the MOSFET closes the circuit, obviously the voltage between these 2 points is going down to 0. That is when the current is flowing through the little transformer and the magnetic field is being generated. A moment later, the IC is opening the circuit and suddenly you're going back to read 390 volts. But if you look at the waveform, actually the voltage is going much higher than 390 volts. We are reading 630 volts here. So what's going on? Well, this has to do with the magnetic field in the little transformer. When the MOSFET opens the circuit, the magnetic field is still there. There's no current flowing anymore, so the magnetic field is collapsing naturally. But a collapsing magnetic field will generate a reverse voltage naturally by the law of physics, and that will add up to the voltage, to the 390 volts that comes from the circuit itself. That voltage can spike up to very dangerous level, over 1 kilovolts of voltage. That's quite a lot. And components probably won't be able to deal with a high voltage, even though it's a very low current. So a switch in mode power supply has a snubber network. It's a number of components, I think it's a diode, a capacitor and a resistor, which are able to clamp that excessive voltage and basically dissipate it, so nothing gets damaged. And once again, you can see that on screen right now. You can see the voltage is spiking up to 630 volts, and then something happens and the voltage gets clamped away down to a more reasonable voltage. And then eventually the voltage will slowly go down to 390 volts when the magnetic field in the transformer has completely collapsed, so there's no reverse voltage being generated anymore. Now, if we have a look at the datasheet of that little offline switcher IC, we see that the absolute maximum voltage that it can withstand is 700 volts. But my oscilloscope is telling me that this component is working at 630 volts. There are momentary spikes, but the absolute maximum is 700, and this circuit is running at 630. It seems a lot to me. So there might be some improvement that we can do to this. We can add a TVS. A TVS is a transient voltage suppressor, and that's probably what we need here. It's a component designed to clamp excessive voltages, excessive spiking voltages. Now, I've selected a component on DigiKey which should be able to clamp that little excess voltage without interfering with the normal operations of this power supply. So the goal would be to try and reduce that spike over, say, 522 volts, so the power supply is working totally fine, and that excessive little spike is being dealt with and dissipated by the TVS itself. The TVS I purchased is a little diode. It's TPS MB650CA-A. Now this has a reverse standoff voltage of 533 volts. That means that below 533 volts, this is not doing anything to the circuit. And if you look at the circuit, I'd like not to do anything to the circuit below around 520 volts. So this should actually be working. What you don't want is this little component to interfere with the normal operations of this offline switcher. So 533 should be okay, and bear in mind that this is not going to clamp perfectly at 533. It will start clamping at 533, but below 533 this is guaranteed not to do anything. I'm going to install it across the legs of the offline switcher, and then we'll test again, and hopefully those extra spikes will have reduced or gone altogether. Is it gonna work, or more magic smoke is going to be released? Let's try it. 3, 2, 1, go. So we had no magic smoke, but unfortunately nothing has changed. That is suggesting that the TVS is just too high. It's not clamping low enough to see any difference whatsoever. I've checked with my thermal camera, the offline switcher is 45 degrees and the TVS is 40 degrees, so it looks like the TVS is not really doing anything. As I said, the standoff voltage is the voltage under which nothing happens, but it doesn't mean that over that voltage the havoc happens. It starts to clamp slowly, and there are much higher voltages where the clamp is at maximum. So I'm going to try with the lower version, that's the 600 version, which has a standoff voltage of 511 volts, which is what you're seeing on screen now, which feels like a bit on the low side, but again, it doesn't start clamping 100% at 512 volts. So let's replace that with the little brother, the 600 version. And whether your project requires a PCB, 3D print, metal sheet fabrication or CNC machining, well then PCBWay is your stop. If you follow my channel, you know I've been using PCBWay for all my PCBs and 3D prints for quite some time, and I've always been very impressed by the quality of the products and the customer service. There is plenty of free projects online which might require a PCB or a 3D print, and placing an order through PCBWay is extremely simple. For a PCB, you'll need to find the Gerber file, and then you upload it on PCBWay.com. The system is very simple, it's more or less automatic. I tend to change the color of my boards, choose a postal service, and PCBWay will ship the PCBs at your place. And take a look at these CPU trays I've recently ordered from PCBWay, they're absolutely fantastic. So take a look at PCBWay.com, the link is also down below in the description, and let me thank PCBWay for sponsoring my videos on my channels, because their help makes these videos possible. So thank you very much, PCBWay. Now let's continue with these power supplies. Let's try again and see what happens. In 3, 2, 1, go. Surprisingly, even the smaller version is not doing anything, and even the thermal camera shows basically no activity whatsoever. But after all, those spikes that we're trying to clamp, they only happen for a split second, a number of times a second, so even if the TVS is doing something, you wouldn't see probably a huge amount of energy being dissipated. Now, I think what happens is that I'm looking at the standoff voltage just to be 100% sure that I'm not interfering with the normal operations of the power supply. But the standoff voltage is where the TVS barely starts to do something. It's actually the breakdown voltage where the TVS actually starts doing something. And the breakdown voltage of this TVS is between 582 and 618 volts, and that's why probably I don't see any change whatsoever. But I don't feel as installing the smaller version here. That would be the 550C TVS, which has a standoff voltage of 468 volts, and I feel that it's going to be too low. I feel I'm going to push my luck. I don't feel comfortable in returning this power supply to its owner with something that might or might not interfere with the normal operations of the power supply. So I think I'm going to fit the 650 volts TVS on this power supply and just leave it there, because that will definitely not interfere with anything, and it might help in case for whatever reason there are some spikes that might be there and might upset the offline switcher over time. But I don't see this as a massive mod that is definitely resolving the problem here. There is though a final modification that we can do to this board to make it a bit more, let's say, serviceable, and that would be to install a Varistor. Now, this power supply surprisingly doesn't have a Varistor. A Varistor is one of these little things here, and it's basically a component which shorts over a certain amount of voltage. So I'm going to install one of these little things here at the back of the board across the live and neutral of the mains coming into the power supply itself. And if there is an overvoltage, well, it will short, the fuses will blow, or maybe the breaker will trip. Now, while I was testing the power supply, I realized that when the fan is switched on, so when the secondary switch is on, the peak between the drain and the source of the offline switcher is actually increasing for a split second. And I managed to capture that with the oscilloscope. What you see on screen, it's that very moment. And you can see the delta Y between 0 volts and the maximum peak is actually over 700 volts. And this is with the TVS between drain and source. So I can imagine that that is probably the reason why those offline switchers don't last forever. Do you think this situation could be improved? Well, if you do know more, please do leave me a comment down below. I'm really curious to see whether there's anything that we can do to make this power supply more reliable. Now, when plugging the fan board on these PCB, I need to be extra careful when the chassis is not in place. The chassis has an indentation for this PCB that you can see here, so it's impossible to misalign the fan connector itself. When I connected the fan board last time, I didn't know that, and I didn't know that the two connectors are actually of different sizes. As you can see, there is plenty of space to just misalign the connector, and that's probably what happened last time when I smoked the board. I made a little green sign in here, green mark, and you can see that when the connector is plugged correctly, the line is in between the little opening on the connector itself. But I can actually plug this incorrectly. So this is exactly what happened last time. You see that now the connector is one row of pins offset compared to where it should be, and can also be offset the other way around. I'm sorry, but this is the proper bad design. Why did they do that? Why not using a connector that doesn't have all display? I don't know. But anyways, this time I'll try to be careful and make sure that this is actually plugged in the middle like this. Thank you, XP Power. The next step for me would be to check the logic of the power supply. In particular, we'll begin with the fan logic and make sure that everything works as expected. This is more or less a 10 years old power supply, so the fan is kind of a consumable, and I think it's a good idea to just get a new one. Now, this is a Delta fan, it's an AFP0612VH, and I couldn't really find an exact datasheet online, and this very fan is not available anymore anyways. I got in touch with Delta sales support and they didn't bother replying, so eventually I ended up purchasing this, which is another Delta fan, same size, same everything. It's a very similar model, it's an AFP0612SH. And according to the data sheets that I found, bearing in mind that I couldn't find exactly this data sheet, they should be more or less identical. Now, why am I being so fussy with just the fan? Just let's swap it, let's get a powerful one and happy days. Well, not really. The fan control board will output a logic signal if the fan fails. And as you can see, these fans are missing the tachometer signal, so the only way for the control logic to realize whether the fan is working or not, I guess it's with power consumption. If the fan is not working anymore, I guess there's no power going through. If the fan is stuck, it will probably draw more current when it's trying to rotate again. So I don't think I can just replace that fan with a random other fan. It might trigger the alarm all the time. So first thing first, I want to make sure that the logic of this fan control board is working, and the logic is coming out of pins 1 and 10, and I've got my multimeter in diode mode connected to those pins. It's basically a transistor opening or closing depending on whether the fan is working or not, and I think the multimeter in diode mode should give me something, and that something will change whenever the fan is spinning or when I stop the fan with my hand. And if that works, we're going to fit this fan and see if that works. Okay, let's turn on the power supply, 3, 2, 1, go. The datasheet for the power supply says that when the fan is fine, the transistor is off. So maybe that means that the fan is okay. Let's try and stop the fan and see what happens. Aha, there you go. It takes a little, oh, that's amazing. It takes a little while, and then eventually the logic says, warning, warning, my fan has stopped working. That's quite interesting. I don't know how this happens. Let me restart the fan. Yeah, and the alarm has gone away, so that works totally fine. Now let's try with the replacement fan that I purchased. The fan is spinning and has been spinning for like a minute, so it looks like the circuit is okay with the fan spinning. Let's see if the circuit reports an alarm when the fan is not spinning. Yes, it's actually immediate. And if I restart the fan, yeah, it's working totally fine. So it looks like this fan is compatible with the logic on that circuit. The next logic I'd like to test is the global DC OK, which is a logic signal coming out of the power supply telling whether the DC output is within 10% of the value that's been set. So I'm wired to the 24 volts now, and the only thing I can try is to adjust the trimmer to hopefully more than 10% below 24 volts, and hopefully the logic here is hard-coded at 24 volts and not at the voltage that I've chosen through the trimmer. So hopefully the trimmer will allow me to put the power supply beyond this nominal range, let's put it away, and hopefully that will change the logic. As soon as I see the logic changing, it means it's working. Let's turn on the power supply, 3, 2, 1, go. My fluke is in diode mode and it's reading 0.169. I've got 24 volts out. Let's try and lower it and see what happens. Yeah. Ah, the logic's changed. Oh yes, the logic has changed. We got 0.169, and if I'm going below more or less 21.6, that's it, 21.7, and the logic has changed. Yeah, so this is telling me that the logic is working. Same test with the global AC logic. Power up, 3, 2, 1, go. That's not good. That is not good. Unless it needs to be switched on. No. Now before I get too crazy with the diagnostic, let me try the other power supply. Fair enough, they were both broken, but hopefully the logic was not affected. Power up, 3, 2, 1, go. Okay, we have no change here. So let me turn it on. Yeah, we got 24 volts. This is still like that. What I'm going to do now, I'm going to remove power. And that must trigger that AC good or not, because the AC is going away. That's the best way of testing it. So I'll remove power in 3, 2, 1, go. No, voltage is going down and the logic is not changing. So either these two power supplies have exactly the same fault, which I really doubt, or I'm testing this wrong. I think I will go with what the manual says. I will put together 5 volts going into this optocoupler and measure as the manual says. Okay, I've recreated exactly what the manual says, which is pretty simple. It's 5 volts going into the transistor inside the optocoupler and back into ground. And there is a 3300 ohm resistor to limit the current, otherwise it would short. I got my multimeter reading the voltage in between the cathode and anode of the transistor, so whenever the transistor is open, I should see more or less the same 5 volts standby. Whenever the transistor is closed, I should read around 0.8 volts. 3, 2, 1, go. Okay, I'm reading 5 volts. That means the transistor is open. Let's turn on the power supply. That shouldn't change anything. 3, 2, 1, go. Exactly. We got 24 volts out. Now, if I remove power, I'm expecting this to change. Removing power now. Well, I wouldn't say, I wouldn't say it's changing. Yeah, eventually it changes, but it should have changed before the regulation was affected. That's the whole point, I think, of the global AC, okay or not? So I've rewired my spaghetti junction here to check again the global DC output, because we know that it works, well, at least on the other power supply, so we take the opportunity to test this one as well. But this time we're going to test with the voltage drop in between cathode and anode. I'm expecting to see about 5 volts when everything is fine, and going down to more or less 0 when the voltage is below 90%. So let's try that and see if that follows that logic. Mains power in 3, 2, 1, go. No, we got 5 volts when there is no output. So I'm expecting these 5 volts now to drop to more or less 0 once we have the output. Let's turn on the secondary. 3, 2, 1, go. Yes, now we got the output here, and the voltage drop has dropped to more or less 0. And again, now at 21.7-ish. It goes back to 5 volts if I'm going back to 22 or something. There we go, 0.2. So the logic is working. Well, I'm totally expecting the global AC power to do something before the power supply completely dies. So maybe we still have a fault on these power supplies. Now, the logic that comes out of this connector here comes from this little section here. Now, this is a bit complicated. It might be a bit out of my league. I tried to do some schematics, but I'm not as good as Marian is. But anyways, I think I managed to get a little bit of understanding of what's going on here. These 3 whitish components are 3 optocouplers. We've seen them before in other videos. An optocoupler is a device which is used to decouple 2 circuits. Inside an optocoupler you'll find an LED, and when the LED is powered, it will shine some light on a phototransistor. When the phototransistor is detecting light, it acts as a transistor and it changes its state. So you can control something which is on the other side of the circuit by shining some light, so there's no physical connection. Now, I've been tracing these components here. The first phototransistor is the global inhibit, it's the on-off switch for the whole power supply. The second optocoupler is controlling the global DC OK signal, and we know that that works, and that's great, because we can use it to check the other one. Finally, the third one is the global AC OK signal, which is the one that doesn't work, so that's the one that we need to take a look at. This I see here, it's an LM339, and it's a voltage quad comparator, and I think this is the heart of our little logic section here. This has 4 channels, and each channel has 2 inputs. One input is a reference voltage, which I'm assuming is fixed, and the other one is the voltage that we want to check. When the voltage that we want to check goes over the reference voltage, that's when the logic output is changing its state. And I think that's what happens here. There must be some reference voltage on the circuit, and some voltages which are coming from around the power supply. One is going to be the DC output, which is being compared to this reference voltage, and when it goes below a certain threshold, it triggers the IC. The IC is driving the optocoupler, and the optocoupler is changing the logic on the other side. So first thing first, I'd like to see how the global DC OK works, because that is working, and that's going to give us a little reference. So I'm going to place my multimeter on the input of the optocoupler where the LED is being driven, so we can check what happens when my logic changes. I'm expecting a voltage change at some point, because the LED inside is being powered or not powered, depending on the voltage output here at the modules. I've got this Zoe multimeter connected to the 24 volts output, and the Fluke multimeter is connected to the global DC-OK optocoupler input where the LED is connected. So we should see something happening here when I'm reaching around 21.5 volts, if I remember right. Okay, we got 24 volts out of it and 1.16 volts at the optocoupler. And I don't know whether that means the optocoupler it's on or off, I don't care. Yes, there we go, 21.22.2, and below that one the logic changes and we're reading 0 volts. Perfect. So let's keep these 1.16 volts in mind, and let's move the probes to the global AC-OK optocoupler and see what happens there. Let's give mains to the power supply. 3, 2, 1, go. 13 volts. That's not... I'm not sure that's what I'm expecting. 13 volts. That's an LED, you shouldn't get 13 volts. Well, clearly the optocoupler is probably fried. That being said, the logic behind this might still be working. I'll show you why. I've got the power supply working, and what I'm going to do in a second, I'm going to remove power from the power supply. Now the 12 volts keeps running for quite some time, so you will see the fan is still spinning even when it's off, and at some point you will see that this voltage will go to 0 volts, and that's a moment before the 24 volts starts decreasing, so just before the loss of regulation. Let me try and demonstrate that. So I'm going to remove power from the power supply. I'm not switching it off from the global inhibit. I'm removing mains from the power supply. So I'm simulating a loss of power. 3, 2, 1, go. Now and now. Yes, so the global DC-OK, which is again, it's 13 volts, it doesn't make sense, changes a moment before the 24 volts disappears. So I think there are some transistors in between the LM339 and the optocoupler. Maybe there's an issue with that. The transistor is shorted and it's passing the 12 volts, which is driving all this logic straight to the optocoupler. Now, first thing first, let me check pin 1 of the LM339, which is the logic output, which is driving the optocoupler, which eventually is going to drive the global AC-OK output. Well, I got my probe reversed, so ignore the minus sign. Well, I'm reading the same voltage, and now I'm thinking about, yes, pin 1 is directly connected to the optocoupler, so that's actually okay. They're not transistors, it's the other one that has transistors in the way, I think. And I think 13 volts actually could be normal if the LM339 is driven by 13 volts, and we can check on another pin. This is the supply of the LM339, and yes, we got 13 volts supply. So the LM339 is powered by the same auxiliary voltage that basically destroyed half of this power supply. No, okay, so ignore everything I said. I got that wrong. So the LM339 is not able to output any voltage. The output of an LM339 is basically the collector of a transistor. It can only sync the circuit to ground. So the reason that we are reading 13 volts of that pin is that that line is being pulled up by a small resistor to V+, and we found that this section is using the auxiliary voltage, the 12 volts or 13 volts as it's reading, which is the one we fixed, the one which overvoltaged. When the LM339 is inactive, well, then we measure 13 volts on pin 1 because the resistor is pulling it high to 13 volts. When the LM339 is active, it pulls pin 1 down to ground, and that's when I'm reading 0 volts across pin 1 and ground. So our logic is working, as you could see. We have 13 volts when the logic is inactive and 0 volt when it's active. So you might be asking, so why was the other one only reading 1.6? Well, that 13 volts is going to an LED, and when you're measuring across the legs of an LED, you're measuring the voltage drop across the LED. And for a working LED, the voltage drop is about 1.2 volts, which is what we were reading on the working optocoupler. So the only way to read 13 volts across the LED of an optocoupler is for the LED to be completely broken, to be open. Then I'm just reading the voltage at those pins. So what must have happened is that the offline switch failed. He generated a higher voltage than expected on the 12 volts line. And again, the optocoupler is on that 12 volts as well. The LED failed, it got burnt by the excessive voltage, and now it's not working anymore. So let me place an order for some more optocouplers. They're still available, thankfully, from DigiKey and Mouser, and we'll replace them and we'll see if that works. I'm confident or optimistic that's going to work as the logic before the optocoupler is working. Here we are simulating the logic line coming out of pin 1 of the LM339, where the line is being pulled up by this 1.8 kilo ohm resistor. We got 12 volts on the other side, and then eventually we end up into the LED, which is inside the optocoupler. Now, as I said, the LM339 can only ground the signal, and right now this is disabled. There is a little switch in here, so the LM339, which is represented by a transistor here, is the collector of the transistor connected to the logic line after the pull-up resistor. Everything is idle because the switch is open, and as you can see across the optocoupler, the voltmeter is reading 1.73 volts. It's a bit higher than what we measured because I can't really configure this LED. There must be a way to do it. It's a different LED, but it's fine. It's 1.73 volts. And if I enable the transistor instead the LM339 by closing the switch, you can see that the electricity is now flowing to ground before it goes into the optocoupler. So my voltmeter is reading more or less 74 millivolts. And this is exactly what we are reading on the working logic circuit. When the logic is enabled, we have 0 volts. When the logic is disabled, we are reading 1.2 volts, which is the voltage drop of the LED inside the optocoupler. Now let's see what happens if we break the LED inside the optocoupler. I have a switch in here. If I open the switch, it's like the optocoupler is not working anymore. It's completely open. It's burnt inside, the LED is burnt inside the optocoupler. And with the logic working, I'm still reading 0 volts, 74 millivolts, which is more or less 0. But if I disable my logic by opening the switch, well, suddenly my voltmeter is reading 12 volts, which is exactly what we were reading before. And this is because my voltmeter has a very high internal resistance. On this one, the simulation is assuming 10 mega ohms, which I think is more or less what happens with the multimeter. So we got 12 volts reaching the circuit, and basically one 10 mega ohm resistor and one 1.8k resistor. So following Ohm's law, we got 2.1 millivolts dropping across the 1.8 kilo ohm resistor, and more or less 12 volts dropping across the multimeter. That's just what Ohm law says. And this is because the LED inside the optocoupler is just not working. If I fix the LED again by closing the switch, then my multimeter is reading 1.7 volts, and most of the voltage is now dropping across the pull-up resistor, 10.27 volts across this 1.8 kilo ohm resistor. So I'm hoping that this is exactly what happens with my circuit. I'm waiting for parts, we'll swap it, and we'll see what happens. Is it gonna work? I hope so, because I really would like to complete this project. Let's give mains to the power supply. 3, 2, 1, go. Yes, I'm reading 1.2 volts. It's the polarity is inverted. That's just why that's the other way around, but that's fine. And I'm assuming that it will stay like that, because that means AC is okay. It means the AC power is okay. If I power up, it probably won't change anything. 3, 2, 1, go. Yeah, doesn't change anything. I left it at 22 volts. Probably a good opportunity to put it back to 24. There you go, 1.2 volts. And I'm assuming that if I remove power, we should be seeing these going to 0 before 24 volts disappears. So let me remove power in 3, 2, 1, go. Yes, it's actually much more than, was that, 5 milliseconds or whatever, but the logic changed just before the 24 volts collapsed. So this is working. Now let's check on the other side and make sure that the optocoupler actually works. The setup is as before, but the Zoe is connected to the other side of the optocoupler. So this should be reading either 0 volts or 4.8, more or less the 5 volts standby, depending on whether the logic is on or off. Let's give mains to the power supply. 3, 2, 1, go. Oh, I left it on. Well, I left it on. We got 1.2 volts at just before the LED, more or less 0 volts after the optocoupler, 24 volts. So I'm going to remove power, And I should see this going down to 0 volts, and that should go up to more or less 5 volts just before the 24 volts collapses. 3, 2, 1, go. That's it, 5 volts and 24 collapses. So yes, the logic is working, and happy days, we fixed it. Yay! Finally, this power supply is fixed. I go ahead and triple check things, then I'll close it up, and we need to move to the other one because the same logic circuit is not working on the other one. I'm hoping for the same fault, but we won't know until we check it. This is the other power supply. I'm wired to the input of the optocoupler where the LED is, and we'll see whether the fault is the same as the other one. Let's give mains to the power supply. 3, 2, 1, go. And yes, we're reading 13 volts, so it should be the same fault as the other one. The LED, it's open in the optocoupler, hence we're reading 13 volts. Well, that should be simple. I shouldn't say it yet, but it should just be a matter of replacing it. So let's go ahead, replace it. Is it gonna work? Power to the power supply in 3, 2, 1, go. And we got 1.2 volts on this side of the optocoupler and this one on this side. I think that's supposed to be totally fine, and it's not gonna change once I power the secondary in 3, 2, 1, go. No, exactly, that's working totally fine. We got 24 volts, and we should see this moving to 5 volts as soon as I remove power to simulate a fail of AC power. In 3, 2, 1, go. There you go, 5 volts and 24 volts collapses. Yes, it's working as well. Fantastic. And finally, I guess we can check the fan logic. So fan logic is also working. What's left to be done on this one is to fit the Varistor and the extra TVS on the standby offline switcher. And while I was finalizing this power supply, just out of curiosity, I double-checked the switching signal of the offline switcher, the 5 volt standby, because I was curious whether I could see the same 700 volts peaks that we saw on the other one and that we couldn't mitigate. And the answer is no, this power supply is working so much better. The signal is exactly the same, but the snubbing circuit is working so much better. I don't have peaks of 700 volts. The maximum I'm getting is about 550 volts, which is so much far away from the absolute maximum of 700 volts. So this is working totally fine, and it's telling us one thing, that the other power supply still has a fault. There must be something wrong with the snubbing section. We'll have to go back to the other one. And I was so happy today when I closed it and I thought, right, this is finally done. Let me install the Varistor on this one. I don't think I need to install a TVS on this because it seems to be working totally fine. Then I'll close this one and we'll go back to the other one. Well, yesterday night when I realized that the other power supply was still faulty, I had a moment of sadness. And then I opened it up just to take a quick look and compare it with the working one. And I noticed something and I thought, could that be so simple? How did I miss that? And I spoke with DJ Mark78 and he also came back with, how on earth did I miss that so obvious problem? So what you see on screen right now is the working power supply, and what you see on screen right now is the faulty power supply. Do you see anything? Yes, there is a broken trace. Now, I can't possibly think how I missed that. It was there from the beginning. I went back to the footage, it's always been like that. The only thing I might remember, I'm not trying to justify myself here, is that I did notice it and I thought, okay, I'll look into that later because there were so many things wrong on this board, and then I just forgot. But anyways, that might play an important role in our fault today. Let me show you why. I got the multimeter in continuity mode, so this pin here is definitely connected to the right hand side of these two components. And these four components here are the snap-in network. We have a diode, we have a Zener diode, we have a capacitor and a resistor. Now this pin here happens to be connected to 390 volts. So if I'm seeing that right, basically that means that without a little trace, the whole snap-in network is disconnected. It's not doing anything. And that would explain very much why on the other power supply we have those massive spikes up to 700 volts. So let's fix that trace. Let's hope that that fixes the problem, and most importantly, that this is the last problem with our power supply. Please work. 3, 2, 1, go. Yes, it's working. Oh my gosh, all that troubleshooting. And the thing was just that the snap-in network was just disconnected. No wonder it wasn't working. Oh, okay, well that's a relief, of course. It's reading exactly like the other one. It's more or less 560 volts, which is totally fine for that IC, which is rated a maximum of 700 volts. So honestly, we don't need the TVS. Not on this one, not on the other one. And the reason why these chips fail, I don't know, it must be something else. It must be a bad batch, a bad design of the chip itself, something. But definitely it's not an issue with the spikes here. So once again, this is fixed. I hope this is the last time I'm saying it. Well, we finally got to the bottom of this power supplies. I was not expecting so many faults from these units, especially the first one. I've lost count of how many components, how many faults we've encountered on both these power supplies. I hope these two power supplies will have another very long life, but I'm really hoping not to see these two very power supplies back on my bench. I think I've spent way too much time on them. That being said, has been fun. I really had fun. Thank you very much again, DJ Marek78, for all your help. I wouldn't have been able to reach this point without your help. And I hope you enjoyed this video too. If you did, as usual, I'd appreciate a thumb up down below, and also consider subscribing to this channel and my second channel if you like this kind of things. Don't forget I'm on Facebook and Patreon, and the links are down below in the description. There is a free tier on Patreon, so no excuses, but if you don't want to join me on Patreon, which is very much understandable, well, maybe you can buy me a coffee, and the link is also down below in the description. If you don't want to buy me a coffee, well, I hope you enjoyed the video. Well, that's it for today. Thank you for watching, and I hope to see you again soon here on my channels for my next videos. Thank you very much, and goodbye. Bye-bye.